Okay, so the last subunit of the calculus, the entire thing, is something called Maclaurin series. And you're given the Maclaurin series in the formula booklet, and you see here it says f of x equals f of 0 plus x times the first derivative at 0 plus x squared over 2 factorial over the second derivative, so on and so forth. And they give you a couple of the expansions. And the question is, what's going on here? What is this? The idea is you can represent any function as a polynomial, but that's not the whole thing. It's not that e of x is going to be totally represented by this polynomial. The idea is around zero. Around zero, the function, whether it's exponential or trigonometric or anything, can be represented by this polynomial. So let's just see this for a second. So let's go to Desmos. Let's just take a look at this. So we're at Desmos. And the idea is you have y like e to the raised to the x. And then you start with so I'm sorry, let's make that f so I can substitute values in there. And then let's call this next polynomial g of x. And from the formula sheet that you saw, take a picture, you're getting it, or look at your formula, look at the idea is that e of x can be represented as like 1, so let's build up 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. I mean, what you notice is that around like 0, like it looks like that polynomial is actually mimicking the exponential function, and we can see that's true. And so, for example, we can test like, f of 0 and g of 0, and we say, okay, you know what, it's the same thing. But the question what you do in a more advanced class is you look at and you determine exactly what is the range, like exactly how far out can I go. So for example, let's change this to a, put a slider in there, a, and then when we start sliding, we can see that the numbers are like they're really close, and the idea is, what is the range where they are really close to each other? So it's like 0.3. So around 0, here we go. At 0, they're exactly the same, perfectly. And as we move away from 0, it's still kind of the same. So in the range, the thing is, once we get away from at 1 and beyond, we see the difference between the two functions diverges. Same thing around here. Like we go back to 0, move from, like we're still, we're still like greater than -1, like 0.7, -0.7. It's still kind of close, right? But then after like -1, the numbers are totally off. And the idea is for the Maclaurin series, the more we expand it, the greater a range. So for example, let's take the next term, plus x raised to the 4th divided by 24. And so we brought it closer together. If I add another term, x, raised to the 5th divided by 120. So the more terms we get, the more we can expand our range of the x values of the polynomial that correspond to the actual exponential function. So that means that we have a method for representing any single function as a polynomial, and that's the point of this lesson.